so my name is Yam. I'm going to talk about deep meta learning, and just before that, this talk is not designed for 20 minutes, so for my next stunt I'm going to try. So the setting for this talk is the following. We have a baseline model, and we would like to get a better one at all costs. And we would like to do it automatically, basically an algorithm that is going to output another algorithm. And talking about whatever the cost, as some of you probably heard, we in deep trading have some hardware expertise to deal with whatever the cost reason. But now let's talk about deep learning because they have superhuman abilities in many fields, for instance, image, speech, and text. But at the end, the only thing they are is some high school math, all right? And where each layer is training on the errors from the layer before it in a process called backpropagation, for instance, LeNet. So let's talk about LeNet. LeNet is a nice convolutional network that is kind of a toy problem in today's terms, but let's just to understand how hard this problem actually is, let's try to optimize the hyperparameters of LeNet, not the parameters trained by gradient descent, the parameters often trained by the neural network in your head. Anyway, so let's not go too far. We would like to just optimize the fully connected layers with grid search. And let's say that we have a GPU that is outputting 1 network per hour, so it's going to take us something like 31 years. And that's only LeNet. No one actually used that. So that's a very hard problem, and every mistake here is going to last for like 2 weeks of not working computations. So the most naive ways for hyperparameter optimizations are grid search or random search, or you can use something that is pretty much the same, but it's called genetic algorithm for a reason, and they work quite good on these domains because those networks tend to be really powerful. So, you know, optimizing the hyperparameters of them with not the most sophisticated algorithm is quite working. But let's talk about Bayesian optimization, which is the next step. Basically, what you do is you sample a couple of vectors for hyperparameters, then you fit your models to fit some sort of a model to those vectors, and basically optimize over this model. Basically, it's done with a Gaussian process to optimize for understanding the distribution and maximizing over the expected. And in real life, there are 3 packages to actually do this for you. The first one is Permint, that is doing everything for you. It's pretty great. It's pretty great, like, for instance, distributing computations and everything. And another one is SMAC, that is doing the same thing, but with, instead of Gaussian process, with a random forest. And the last one that is not special at all, it's called Bayesian, but it's very, very popular in deep learning community. Everyone in ICLR is talking about Bayesian, so it needs to be in a presentation. All right, so the setting for supervised learning is that, wait a second. Since when are we allowed to use random forests here? I mean, we all learned this in Toar Rishon. Since when are we allowed to do that? And some questions. Can we use other models? Instead of random forests, and maybe we can use the certainty of a model as a variance, and maybe we can just set the variance to 0 and just hope for the best and like predict with the model, or use a different learning algorithm, or brute force like all the models to see if one of them doesn't work. What's going to happen? I'll tell you what's going to happen. You're going to get better results because I tried. So. But more on that later. Let's fix the previous slide. Basically, we're not doing Bayesian optimization. It's model-based optimization. It's a search problem, basically. We're trying to maximize something into the future and doing so by learning some sort of a policy that maximizes something into the future. I don't know about you guys, but I've seen this somewhere. So this link between reinforcement learning and Bayesian optimization is extremely crucial for this talk, for the rest of the talk, if we're going to ever make it. So yeah. Anyway, before we continue with this, anyone know any other algorithm we can try to optimize hyperparameters with? Well, I heard about one. Let's use gradient descent for hyperparameter optimization. So how do you actually do that? Nothing here is actually differentiable, except for if you formalize it in this term. Basically, stochastic gradient descent is a function that is mapping from an init condition to a series of parameter tensors, and that's it. The tensors are differentiable by definition. Gradients are differentiable by definition. So basically, everything is differentiable. What you do is you take your network, simulate a couple of steps into the future, stop somewhere, go all the way back, and compute the gradients with respect to whatever step that you are. And in the first step, you can take 1 step back, because now you have all the gradients to tune the hyperparameters. But and yeah, they have results. Anyway, talking about that, it's very computationally expensive because what you do is you simulate forward and backward training and training and training, and it's very computationally expensive. But if you think about it, you have residual changes on every step. You don't have to take many steps into the future. So basically, you can take one step, compute a gradient, and change the hyperparameters accordingly in this improvement of this paper, and they have results as well, and they look nice. Anyway, this is nice, but if you think about it, you cannot just use your validation set for that because you have now 2 learning algorithms and too many degrees of freedom, and basically your algorithm will pretty much converge to like 0 because it can. So another improvement to that is to use another subset of validation set for the meta learning and the normal validation set for your model. And they have results. And I was myself at this talk in ICML, and it was a really good talk. I highly recommend people who are into this field to watch this talk. Nice approach. All right, my approach. Nothing really fancy. Let's just use what we saw until now, reinforcement learning to optimize the hyperparameters. We can choose whatever network that we want. I use deep learning just because. And there are certain improvements to this algorithm like DDQN or DDQN, dual double, and prioritized replay, A3C for the why not. But actually, really nothing here is really fancy. And my approach 2.0, I lied, now it gets fancy. We all know that under certain constraints, genetic evolution strategies are somehow isomorphic to the approximation of gradient ascent, not descent, ascent, going up. So why won't we do that instead of reinforcement learning? It's much less computationally expensive. So yeah. Anyway, that's the code if you're interested. So let's talk about ensembling of models instead. All right, so naive ways to ensemble models are the following: majority vote or average, bagging, which is basically subsetting the training set a couple of times, or boosting, taking the errors into consideration in bagging. But before that, there is one ensemble that is worth mentioning. It's pretty much everywhere. In case you've been living under a rock for the last couple of years, XGBoost is pretty much dominating all of the computation, competitions. And basically what you do is you have a random forest and you want to boost the prediction a little bit more. So what you do, you put the weights on the leaves of the ensemble. And how do you train the weights? How do you train weights? Gradient descent, because yeah. And it's not differentiable, so what we do, an approximation of second order, and it's going to be fine. Anyway, it's the most popular machine learning algorithm, I think, ever. Anyway, back to ensembling. So let's say that you have a training set, you have a set of classifiers, and you want to train them all. So what you do, average, right? Yeah. So what happens if you don't do average? You put another classifier here on their prediction and use that. It is called stacking. It is extremely popular in competitions. And basically what you do is you train a better classifier, then you train another classifier based on the predictions of the other classifiers. And if you want to do this in real life, there is the package called MLExtend, and it is doing it for you. Basically, you have a stacking classifier, just throw your models in, and it will take care of anything for you. But it has a problem. It allows you to do only one layer, so I extended MLExtend to infinite amount of layers. It's in my GitHub. Have fun. So the process of machine learning goes the following. Basically, you get some data, then you represent it in some sort of form, feature extraction. You build a model, you tune your hyperparameter, and you evaluate. And then it doesn't work, so you build another model or find out a new feature representation for your model, and basically you keep going over and over and over in this machine learning jail forever. Unless you're using AutoScikit-learn to do that for you, and yes, this is a real thing, AutoScikit-learn. So those of you who are not familiar with AutoScikit-learn, please be. All right? Now back to deep learning ensembles. This is very computationally expensive, so we are not going to just take models and train them and hope for the best. Maybe, because the training is sequential, maybe we can just take a snapshot of the same model. So instead of actually doing that, because your model gets better over time, why would you take a not good model? One of the things you can do is to increase the learning rate during your training. And one of the most popular ways to do so is with the cyclic learning rate equation. And basically you take a snapshot with the cyclic learning rate equation, and it works really, really good. That's their real paper from ICLR last year, and it works really good. All right, so now you have a lot of models, and you want to know which ones are good because you're training all of them and predicting with all of them. So basically what you do is you simulate with all of them, with all the subsets, and basically trying to find which models perform the best in their subsets. And this paper is doing the most naive way possible, just take the average. So basically, we have a way to choose the best models, and we have a way to choose the best parameters. Can we do this together? And the answer is yes. There is a package that is doing it for you. Spearmint for before got extended to Spearmint Salad that is doing exactly that for you, so have fun. And last but not least, is this necessary? And this paper is claiming that not really, because deep learning is extremely powerful on its own. The predictions are pretty much correlated most of the time, so by showing a lot of results that we are not going to cover here, they say that, you know, only if you really need to. But an approach that do work pretty good is tree ensembling, and it's less popular, and I highly recommend you guys to try it. I have in my own GitHub the graph ensemble for doing graphs of ensemble, training on which predictions of everyone. But that's a nice approach to take as well. I think it deserves its place here. Another important aspect is how do you actually combine deep learning predictions with like handcrafted features. I'm good. Deep learning predictions with handcrafted features. And the way they do this in this paper, it's a terrible paper by the way, they take the predictions, they just append it to the Flutter and like wrote a full paper on that. But it really raises the question, how do you actually do that? I mean, how do you take deep learning and like combine it with handcrafted features, and you can do it like that, or you can add it to the features, to the filters of the convolution in many other forms. But basically, it's an open question. All right, ensembling is nice, but let's talk about the gradients themselves. Basically, talking about a paper, learning to learn by gradient descent by gradient descent. And this is not a joke, this is a real paper. And basically what they do in this paper is instead of computing the update rules with, you know, a normal gradient descent, they use another network to optimize over the update rules from pretty much nothing, because everything is differentiable with the LSTM from nothing all the way to the update rule of the LSTM. For those of you who think this is a rocket science and cannot be done never in real life if you're not Google, it's in my GitHub. The only thing you need to do is change one line in Keras, and that's it. Have fun. All right. Another paper worth mentioning by a close friend of mine, Eli David. He is, by the way, the founder of Deep Instinct. They gave a good talk in this conference as well. What he's doing in this domain, he's basically using genetic algorithm over the tensor weights, where he switched the mutation by backpropagation. And basically what he do is he train a network and, you know, switch the filters between a couple of networks, and then, you know, backprop all of them, change it a little bit, sweet it, and it doesn't have results like all the other papers. All right, my approach. You all know those, right? Not if you do. Yeah, okay. Scary equations. Let's look at them from a different perspective. We can look at them from this perspective of graph, and now it's pretty much shouting to use genetic programming to learn the update rules for the optimizers of the network. And there have been some improvements to this algorithm. And let's talk about building an architecture from scratch. All right, the motivation for that is clear. We know that architecture influences results greatly, but we can, all right? So, starting slow, neat, neuroevolution. Probably most of you have seen this video already. Basically, you learn the weights and the architecture with one genetic algorithm. It is nice, but it's a toy problem. You can extend it really easily to convolutional neural networks. Basically, what you do is you have like a vector representing your layer, and, you know, switch layers and stuff with other chromosomes. But then you probably think, all right, yeah, that's not deep learning. Let's use like the graph structure of deep learning. You learn the skip connections as well with genetic CNN. Then you get results somehow. They are better than anyone, like all the papers. But then you can go like with genetic programming, you can go all the way crazy and optimize the whole network graph to something, you know, like that. But none of those are really interesting because they're not really novel, it's just using a lot of computations. But if you split your network and look at it from the wide perspective, basically what you do is you can look at the nodes themselves, and, you know, some of them update with skip connection, and some of them happen with feed forward and everything. But if you look at it from the right perspective, so from the wide perspective, you can do a lot more, and they have results as well. And Google is taking another completely different approach with DeepMind. Basically, they have a set of known blocks, and they just compute the paths between them and compute the gradients with respect to whatever the path they are on, and inventing a new world called super neural network, which is a new word. Anyway, extending it one step further, you don't have to use a complete block. You can do it with all of the layers themselves. And train it now with reinforcement learning that is new in this domain, in those papers, and you get pretty nice results, but it's not the end. You probably think, all right, that's nice, but how do you optimize the whole graph of deep learning? Yeah, they got results. And here comes someone from Google who's doing crazy research, someone called Zoff. We met in ICLR last year, and his whole research is about learning to learn and learning architectures of deep learning. Basically, what he's doing here is learning everything, like encoding everything to one big stream and predicting this whole stream with an LSTM. Right? This is what he's doing. And at the end, he gets those funky graphs that are pretty nice to watch, and he gets good results over like many data sets, and it gets more crazy than that, like the Google way, and he's optimizing everything and gets to the point where he optimized the whole network graph to learn very funky architectures. All right, and this is real poster from ICLR, and he's done some prior work. This is the prior work for something else that he's done, basically in reinforcement learning or a genetic algorithm, mainly in that it's very hard to do hierarchical learning, meaning that you can learn a network, but you probably will converge to some sort of a local minima because it's very hard to use that. So one of the things that he's done is that instead of actually optimizing the whole network from scratch, you optimize a couple of blocks and then use these blocks in reinforcement learning, like hierarchical way, to build a whole network out of them. So that's a nice approach. And last but not least paper from this presentation is the following one. Instead of actually using one network to predict the whole network, you use a couple of them in hierarchical ways. One of them is predicting how to widen, and one of them is predicting how to deepen, and basically you have another controller that is choosing which step to do each time, and each step is like, the step is predicting the next step to take, so it's another layer of meta. And they have nice results, but I don't have time to go over them. Yeah. All right. Last paper, 30 seconds. This paper is about training, again, learning the architecture, but learning architectures is very computationally expensive, so what they've done is predicted the weights as well, and not just the architecture, in order to avoid bad architectures as a whole. It's a nice concept, and it's pretty, crazy. Conclusions, I'll get only to the first one. Is this for everyone? I mean, everyone should do this craziness, and the answer is no. Unless the accuracy is like directly influencing, I don't know, profits or publication or something, you don't have to do that. Another important thing I want to say, those models tend to be pretty powerful on very non-native things. It's pretty impressive to see those models trained to predict and create another models. And I'll not go through all of the conclusions, but I think you got it, and I think we'll end here. Thank you.